Hi folks, it's Mr. Solona again. Today we're going to be looking at the Newton's second law lab, and the objective of this lab is to see how changing the mass of an object can affect its acceleration and how changing the net force acting on an object can affect its acceleration. And we're going to want to test those two things independently of each other. You might already have some ideas about how changing the mass of an object might affect its acceleration and the net force and how that affects its acceleration, but we want to be able to quantify that. So what we're going to do and what we're going to need for this lab is we're going to need a scale, we're going to need the vernier track, we're going to need the GoDirect sensor cart, a set of masses, and the masses that go along with the cart. We're going to need some string with a loop on the end so we can attach masses to it, and we're going to need the ultra pulley attachment for the track. So what we're going to do to get started is we're going to take the mass of the cart. So if I take my cart, put it on the scale, I had done this previously, and I got 290 grams, but you're going to need to measure the mass of your cart. Okay, and then just check to see the masses of these. They should be 125 grams, but you're going to want to check that. I definitely did for mine. But check to see that each of these is 125 grams. Okay, then we're going to need to connect our cart to the Chromebook or the computer. So I'm going to open up Vernier Graphical Analysis. I'm going to go to Sensor Data Collection, and I'm going to want to turn on my cart. Red light comes on. I click on that Sensor Data Collection, and it will load. Hopefully it will find my cart is on. So usually it will scan, and you want to look for this. So you want to make sure that the ID number on the cart matches the one that's on your screen, especially if you're working in a lab where other kids are working. They might be using another cart, and your Chromebook might try to connect to another person's cart. So you want to make sure you're connecting to the proper cart. I'm going to click this, and it's going to ask me what I want to track. For this lab, because I'm looking at acceleration, the position sensor is really what I need for that. So sensors channels, it says position. I'm good to go. I'm going to click done. And I'm going to change this so I only get one graph on the screen. So I'm going to change it to one graph, and I'm going to make this graph a velocity graph. So I'm going to look specifically at the velocity of the cart. So that's all set up. What I'm going to do now is load the cart up with all the masses. So this should be 500 grams of mass, 125 grams for each one. But again, you want to double check that. I'm going to load that up. I'm going to attach the string to one end of the cart. And I'm going to bring it down here so I run the string over the pulley like this. And I'm going to take a 50-gram mass out of my mass set, and I'm going to hang that here. This way, I'm going to control how much force is actually pulling the cart, because I'm going to use this weight to hang every single time. So it's not like me pushing the cart and not knowing how hard I'm pushing. I can control and get exactly the amount of force that I want every single time. So I'm going to put this here, and then it's ready to go. From this position, I'm going to click collect, and I'm going to allow the cart to roll across the track. So I click it like so, and release, and just let it go. And the part that I'm looking for is this portion here. You can see that the cart definitely accelerated. Its velocity is changing pretty consistently, in fact. All right, what I need to get from this is the slope. So what I'm going to do is click on the graph tools. And there's a couple ways I could do this, but the easiest way is to hit the tangent button and then just click a portion of the graph where it's very much a straight line graph and get that slope. So you can see here it's 0.534 meters per second squared. I'm going to record that in my data table. So I'm going to go back to my data table here. And you can see here I've already filled in the mass of the cart. And I'm going to put in the measured acceleration, which is what we had a minute ago. It was 0.534 meters per second squared. So I'm going to put that in here. And then I also want to put in the mass on the cart, which was 500 grams, which is 0.500 kilograms. Okay, so the total mass of the system, I'm going to actually add this plus this and the 50 grams that was hanging from the string. So that'll go into that total mass of system column. We can work that out later on, but we'll add all of those together. The theoretical acceleration and the percent error are things that we can talk about later on. So for the additional trials, what we're going to do is we're going to vary the mass on the cart. So instead of using 500 grams on the cart, I'm going to remove one of these, and then I'm going to repeat the same exact process again, and I'm going to put the new measured acceleration in with the new mass on the cart. So in this case, it would be 0.375 kilograms. So you're going to work that through, removing each one at a time until you get down to the empty cart. Okay, at that point, you have all the data you need for part one, where we're varying the mass and seeing how does that affect the acceleration. Okay, for the force applied, I'll just do the one trial here, but they're all going to be the same. We hung a 50-gram mass from the string. 50 grams is 0.05 kilograms. Well, that's not a force, but the weight of that would be the force that's pulling down on the string. So 0.05 kilograms times 9.8 meters per second squared gives me 0.49 newtons. And that is my force. And all of them in part one are going to be the same exact force. So that's all of part one. Now, for part two, instead of varying the mass, we're going to vary the applied force and keep the mass of the system constant. Okay, so for this part, we're going to remove these weights. And instead, I want to use a set of masses like this. So what I'm going to do is I'm going to take a 200-gram mass, a 100-gram mass, and the 50-gram mass that I had on the string, and I'm going to place those in the cart. And I'm going to take a 20-gram mass, and I'm going to put that actually on the string this time. So we have this set up again similarly. Let me grab this. Okay, so we have 20 grams hanging from the string, and we have a 200, a 100, and a 50-gram mass in the cart. And you'll see why we're going to do that in a second. All right, so again, we go back to vernier, and we're going to, we're going to collect the data. So I'll hit collect, I'll release the cart, and we'll do the same thing. Just like that. And I can click stop here if I want once it's at the end of its motion. I'm going to take the slope of this part of the graph just like before. So graph options, and I'm going to go to tangent. And then I'll click on a portion of the graph that has roughly a straight line. So here I'm getting 0.295 meters per second squared. So I'll go back to my table, and I'm going to put in 0.295 meters per second squared there. Okay, keep in mind the mass of the cart is still the same, so all of these numbers here would just copy on down to this part. Okay, now if you think about how much mass did I have on the cart, I had a 200, a 100, and a 50. So it's 350 grams. That's 0.350 kilograms. Okay, and we talked about how to calculate weight. So this time you would do 20 grams, that's 0.02 kilograms, times 9.8. That's the force that goes in. Now here's where it gets tricky. We have to take the 20-gram mass that was on the string, and we're going to put that on the cart now. And we're going to take the 50-gram that was in the cart, and we're going to put that on the string. And the reason for that is we want to make sure that the total mass of the system is still the same. Remember, it's not just the cart and these weights that are moving. This mass that's hanging from the string is also moving. So we have to make sure that the combined mass of everything is still the same. So we did that by swapping the masses. So I'll run this again, and we'll get the data. Like so. I'll click stop, Again, I'll find the slope just like before. This time I get 0.703 meters per second squared. So I'll fill that into the table over here, 0.703. And if I think about how much mass I had on the cart this time, it was a 200, a 100, and a 20. So that's 0.320 kilograms. Like that. Oh, nope, 0.320. There we go. 2 more trials. What you'll do is swap the 50 and the 100 gram masses and repeat, and then swap the 100 and the 200. So this way, all 4 of the masses, 20, 50, 100, and 200, all got hung from the string, and all of them were in the cart at one point. Okay, so you'll have 4 trials in part 2, 5 trials in part 1. Once you have the data, what you're going to do is you're going to end up making 2 graphs. We wanted to know, how does acceleration depend on mass? So we're going to take our theoretical or measured accelerations, and we're going to graph them on the y-axis versus our total mass of the system. Sorry, I was pointing in the wrong direction. The total mass of the system. Okay, remember that total mass is going to be the mass of the cart, the mass on the cart, plus the mass on the string. So we'll add those together, put them in here, and we'll make a graph of that. Then, in the second part, we're going to make a graph of acceleration versus the force applied. So what we'll do is, this will go on the y-axis, the measured acceleration. The force applied will go on the x-axis. Remember, that's the weight that's hanging from the string. And then you'll make a scatter plot graph of that. Using that data, we'll look at what are the actual mathematical relationships that we see in the data.